Good morning, students. Welcome in next lecture of Math F242 Operation Research. Audio video is okay.
Yes, sir.
So today we are going to start the new model MM1 FCFS Infinity Infinity. In last class, I have covered the self-service model, that is the MM Infinity FCFS Infinity Infinity. So today we will cover the MM1 FCFS infinity infinity. What is the candle notation? This is the infinite infinite population. This is the infinite capacity, infinite system capacity. Then this is the service discipline, service discipline. This is the number of server, number of server. So it is given to you. There is one server. That's why this model also known as the single server queuing model. Single server queuing model, right? Then after, since it is the Markovian model, Markovian or Poisson queue, presently we are studying the Poisson queue. So here the service time follow the exponential distribution with parameter mu, and this inter-arrival time also follow the exponential distribution with parameter lambda. That is the arrival follow the Poisson process. Poisson process. So if we have this situation, we call it as a single server queuing model, right? So this is the first model. So in this case, we have we have lambda n is equal to lambda and mu n is equal to mu. Means for all n, there is no change in the rate. That is for the n is equal to 0, 1, 2, and 3, and n is equal to 1, 2, 3, and so on. So if you make its transition diagram, state transition diagram, so initially we have the 0 customer, then 1 customer, then 2 customer, 3 customers. So we know that we represent the state by the node and number of customer we write in the that node. And transition we denote by the arrow. So customer are joining with the rate lambda, customers are joining with the rate lambda, customer are joining with the rate lambda, and here the customer are joining with the rate lambda. Whatever the state, the customers are joining with the same rate lambda. Similarly, whatever the number of customers available present in the system, all are getting the service with the rate service rate mu. So either you solve it by the birth and death process, or directly you can write using the result of the birth and death process. So there we know Pn is equal to what? Cn into P naught. Cn into P naught. and it is given to you, and all the mu's are mu, mu, and mu. Or this can be written as rho to power n, where rho is equal to lambda upon mu. So see, there is lagging, I think. You people are also facing the lagging
Yes, sir.
in the voice also.
Yes, sir.
Now please observe. So I was talking that the Pn is equal to rho to power n into P naught for n is equal to 1, 2, 3, and so on. So now we have to compute the value of the P naught. So from the normalizing condition, from normalizing condition, what is the normalizing condition? We know that sum of Pn is equal to 1 for all n is equal to 0 to infinity. So this can be written as P0 plus P1 plus P2 plus Pn plus is equal to 1. So from all, if you take the P0 common, so inside we have 1 plus rho square plus rho to power n and is equal to 1. So here, this is the infinite geometric series with the common ratio. So this is the geometric progression series with common ratio rho. And rho is what? Rho is lambda upon mu. And we know that effective arrival must be always less than the effective service rate. So that's why this ratio is this rho value is less than 1, since lambda is less than mu. Effective arrival must be less than the effective service rate. So this, if this is the infinite geometric series, so P naught, this can be written as 1 upon 1 minus rho. 1 upon 1 minus rho, and it is equal to 1. So this will give you P naught is equal to 1 minus rho. So that is the P naught is what? P naught is probability that there is no customers in the system. There is no customer in the system. That is the P naught. So from the P naught, Now we can compute the state probability as Pn is equal to rho to power n into P naught. That is Pn is equal to rho to power n 1 minus rho for n is equal to 1, 2, 3 and so on. So that is our state probabilities. That is our state probability. So this is the derivation through the through the birth and death process. If I ask you, write the Chapman Kolmogorov differential difference equation. So how we can write? We know that how we can write whatever the outgoing, that is with the negative sign, whatever the incoming, that is with the positive sign. So if you want to write for the nth node, generally we write for the general node, nth node. So outgoing are mu and lambda, incoming are this mu and this lambda. So its equation will become if you want to write the transient equation, so dpn t by dt is equal to outgoing lambda plus mu pnt plus lambda pn minus 1 t plus mu pn plus 1 t, and for the zero node dp0 by dt. So whatever the outgoing, that is the lambda p0t, whatever the incoming, that is the mu from the p1t. So here we have the, you can notice for the zero, this is the outgoing, right, outgoing, and this is your incoming. So outgoing with the negative sign and incoming with the positive sign. And when we are writing the differential equation, so there must be the initial condition. So initially we assume that initially there is zero customer. So P00 is equal to 1 and Pn0 is equal to 0 for n is equal to 1, 2, 3 and so on. Means always in any system, there is no customer at the t is equal to 0. So now we have to solve this system of differential difference equation. From here, if you want to write the steady state equation, so steady state equation means t tends to infinity or d by dt is equal to 0. So this will become minus lambda plus mu pn plus lambda pn minus 1 plus mu pn plus 1 is equal to 0 and minus lambda p0 plus mu p1 is equal to 0. And for the steady state, we know we have the normalizing condition, summation of pn n is equal to 0 to infinity is equal to 1. So means you can solve this system of linear equation independently to get the result whatever we have derived through the birth process. So either you solve this system of linear equation or you derive through the result of the birth and death process. So generally if we know the states, if we know the condition of arrival, or if we know the state dependent arrival rate and the state dependent service rate, so directly we can apply the birth and death process. So after having the state probabilities means Pn is equal to rho to power n 1 minus rho and P naught is equal to 1 minus rho for n is equal to 1, 2, 3, and so on, we can compute the system performance. So first system performance, we always take the L. What is the L? It is the expected number of expected number of customers in the system. Expected number of customer in the system. So we denote it by the En. We denote it by the En. That is the means N is the state of the system or number of the customer in the system. So its expected value. So what is the basic formula of the L or En? Anyone please tell?
Summation n into Pn.
Yes, summation n into Pn, where n vary from 0 to infinity. So this will become P1 plus 2P2 plus 3P3 plus 4P4 plus NPN plus and so on. Right? So up to infinity it will go. And all the values we have P1, P2, P3, P4 already we have computed. So in all, we know that we can take P naught common. So P1 is what? Rho P naught. P2 is what? Rho square P naught. So 2 rho square. P3 is what? Rho cube. P4 is what? Root power 4 P naught. Similarly, N and Pn is what? Root power N into P naught. So P naught we have taken common. So now this is the APGP series. So this is the APGP series. So let this sum we are representing as a S. S is equal to rho plus 2 rho square plus 3 rho cube plus n rho to power n and so on. If you multiply this S by the rho, so this will become rho square plus 2 rho cube plus 3 rho to power 4 plus n rho to power n plus 1 and so on. If you perform the first minus second, 1 minus rho into S. If you subtract the second from first, we have the 1 minus rho into S. So it will become rho 2 rho square minus rho square, that is the rho square, 3 rho cube minus 2 rho cube plus rho cube and so on, plus rho to power n and so on. So this is again the geometric series with the common ratio rho and first term rho. So here we have the sum is equal to, this is the geometric series with r is equal to rho and first term is equal to rho, a is equal to rho. So what is the sum of this? Sum will be the, yes, anyone? And we know that rho is less than 1. Rho is less than 1. So sum will be a upon 1 minus r. Yes, correct. So it will be the rho upon 1 minus rho. So here S will become rho upon 1 minus root whole square. That is our S. So when we put this S here, so it means it will be the P naught and rho upon 1 minus rho whole square. And what is the P naught? P naught is 1 minus rho and rho upon 1 minus row whole square. So 1 minus row and 1 minus row is cancel out. So here the L is equal to row upon 1 minus row. And when we put the value of the row as lambda upon mu, 1 minus lambda upon mu. So here L will come lambda upon mu minus lambda. So that is the another formula for the L in terms of the arrival rate and the service rate. So that is your L, expected number of customers in the system for MM1 FCFS infinity queuing model. Now next we compute the variance of n. Means n is what? State of the system, that is number of the customer in the system. So now we compute the Vn, and for the variance, you know what is the computational formula? That is the E of n square minus square of En. Square of En. That formula we know. So En already we have computed. En already we have computed. That is the L square. L square. Now we have to compute the E of n square. So E of n square, if you compute, what is the basic formula? It is the summation value n square into corresponding probabilities. N square into Pn, n is equal to 0 to infinity. So that is 1 square P1 plus 2 square P2, 3 square P3, n square Pn, and so on. So Pn value is, you know, root power n into P naught. So if you take the P naught common, so it is the 1 square row, 2 square row square, 3 square row cube, 4 square root power 4 plus n square root power n, and so on. Right? So again, this is the APGP type series. Let us assume, let this sum is equal to S. So S 1 square row, 2 square row square, 3 square row cube plus n square root power n, and so on. If you integrate this S with respect to row from 0 to row, if you integrate this S with respect to row from 0 to row, so here we have the row square by 2, or instead of assuming this S, in the first series we can take the row common also. Instead of assuming this S, you assume, means just one line we have to add. So here P naught row, if you take common, so inside we have the 1 plus 2 square row, 3 square row square, plus 4 square row cube and n square row to power n minus 1 and so on. Now assume this as a s. So s is equal to 1 plus 2 square row plus 3 square row square plus 4 square row cube plus n square row to power n minus 1 and so on. Now you integrate this s with respect to row from 0 to row. So first one will give you row, second one will give you row square by 2, 2 and 2 cancel out, so 2 row square. Third one will give you row cube upon 3, that is the 3 row cube. Similarly, nth one will give you row to power n upon factorial n or upon row to power n upon n, right? So n and n cancel out, so it will be the n into row to power n and so on. So if you compare this right hand side, so this right hand side just you have solved. What is the value of this right hand side? Just you have solved this. This right hand side is what? S is equal to, right, this one, row 2 row square plus 3 row cube plus n row to power n, and its sum we have seen it is equal to row upon 1 minus row square. So from the above we can write it as a row upon 1 minus row whole square. From above we can write it like this. Now on differentiating with respect to row, if you differentiate with respect to row, so on the left hand side we have the s, and on the right hand side we have the 1 minus row whole square. Differentiation of the numerator row as a 1 minus row 2 1 minus row minus 1 upon 1 minus row power 4. So 1 minus row will cancel out. So 1 minus row plus 2 row upon 1 minus row cube, that is the 1 plus row upon 1 minus row cube, that is its sum. So when we put p naught, so here we have the p naught p naught row into 1 plus row upon 1 minus row cube, 1 minus row cube. So this p naught and this will cancel out. So it is the row into 1 plus row upon 1 minus row whole square, because p naught is what? 1 minus row. So row 1 plus row upon 1 minus row whole square. That is the value of the En square. We have to compute the Vn. Vn is what? En square minus square of En. Variance you know how to compute. So just we have computed this value as row 1 plus row upon 1 minus row whole square minus, what is the value of the En? Row upon 1 minus row and whole square. En we have computed before this, so it is equal to row upon 1 minus row. So it will become 1 minus row whole square, 1 minus row whole square, and we have the row plus row square minus row square, row plus row square minus row square, so it will cancel out. So Vn is equal to row upon 1 minus row whole square, that is our Vn. Is there any doubt? Is there any doubt you want to ask anything? Then after, what can be the other parameter system performance indices? Now, if you have to compute the LQ, what is the meaning of the LQ? That is the EQ or expected number of customers in the queue, right? Expected number of the customers in the queue. What can be the basic formula? Anyone please tell? Expected number of the customer in the queue, n minus s into pn. So it is the summation. General formula is n minus s into pn, n vary from s to infinity. Because this is the single server model, so this will become n is equal to 1 to infinity, right? N minus 1 into pn. That is the basic formula. So this can be written as summation n is equal to 1 to infinity npn minus summation n is equal to 1 to infinity pn. Now please observe what is the first summation. What is the first summation? Yes, it is the L, n into pn. From n is equal to 0 to infinity, either you write, or 1 to infinity you write, both are the same thing. So it is the L. And what is the second summation? What is the second summation? Not 1, not 1. Please see carefully.
1 minus P naught.
1 minus P naught. Because 1 is summation of all probabilities. So it is the 1 minus P naught. 1 minus P naught. So L minus 1 minus 1 minus rho. P naught we have computed as a 1 minus rho. So here 1 and 1 cancel out. So this will become L minus rho. That is the another formula. LQ is equal to L minus rho. So from here we have now one little formula. What is that? L is equal to LQ plus lambda upon mu. That is the same thing, right? LQ is equal to L minus rho. So it verifies the little formula also. Now, what is the value of the L? Rho upon 1 minus rho. And what is the this? If you write like this, so here we take the LCM 1 minus rho. So rho, here we have the rho minus 1 plus rho minus rho plus rho square. So rho and rho cancel out. So here we have the rho square upon 1 minus rho. That can be written as rho upon 1 minus rho into rho. That is the L rho also. So LQ is equal to L into rho. Right? LQ is equal to L into rho also. We have one formula. Another formula you have derived as LQ is equal to rho square upon 1 minus rho, that can be written as lambda upon mu whole square upon 1 minus lambda upon mu. That can be written as LQ is equal to lambda square upon mu square. So lambda square mu and mu minus lambda. So that is another formula for the LQ. Lambda square upon mu square, right? And 1 minus lambda upon 1 minus lambda upon mu. So that can be written as lambda square upon mu into mu minus lambda. So that we have computed the L and LQ. From here, if you have to compute the effective arrival rate, effective arrival rate. So effective arrival rate we denote by the lambda bar. And what is the basic formula of the effective arrival rate? It is the summation lambda n into Pn, n vary from 0 to infinity. And we know that for all state, lambdas are lambda. So summation n is equal to 0 to infinity, it is the lambda into Pn. That can be written as lambda summation n is equal to 0 to infinity into Pn. And what is this value Pn? This summation is what? It is the sum of all
One.
probability that is equal to 1. So it is the lambda into 1, that is the lambda. So lambda bar is equal to lambda. Now from here we know what is the W. W is the ET, expected waiting time. Expected waiting time. Expected waiting time, and expect by the little formula, expected waiting time is what? L upon lambda bar. So L upon lambda, because lambda bar is what? Lambda. So we have the L upon lambda, and L is what? Lambda upon mu minus lambda into 1 upon lambda. So lambda and lambda cancel out. So here we have the 1 upon mu minus lambda. That is the W. Similarly, if you have to compute the WQ, that is the expected waiting time in the queue. Expected, here you complete the line in the system. So it is the what? It is the expected waiting time in the queue. Expected waiting time in the queue, that is the LQ upon lambda bar, and LQ just now we have computed as lambda square upon mu minus lambda 1 upon lambda. So 1 upon this lambda and this lambda is cancel out. So here we have the lambda upon mu minus lambda, or rho upon mu minus lambda. So it is advised to all that you write all the formula at one place, so that when we do the numerical example, at that time you have not to revise or your papers. So it's better you write at one place. So here we have computed the expected waiting time in the system and expected waiting time in the queue. So if you have to compute proportion of time, the server is idle. So when the server is idle, when the server is idle, when there is no customer in the system. When there is no customer in the system, so that is it is equal to the P naught. When there is no not at the t is equal to 0, it is ideal, but here we are talking for the steady state. So when the steady state, so it is independent of time t, right? Is it true? Means it is true that at the t is equal to 0, server is idle, but not always. So a server is idle when there is no customer. That is equal to P naught. And P naught is what? 1 minus rho. 1 minus rho. And similarly, if you have to compute the proportion of time, the server is busy. Server is busy. So it means when we have the customer in the system, so it will become the 1 minus P naught, or that is the rho. That's why, and rho is what? Lambda upon mu. That's why this rho is also called the utilization factor. Utilization factor. This rho is also called the utilization factor. So in this way, we can compute the different performance measures. So for any performance measures, you want the repetition. So here we have completed the MM1 FCFS infinity. Let us have some problem. If we have this problem, RTB repairman. What is the meaning of the RTB repairman?
Single server.
Single server. So this give you S is equal to 1. Repairs a TV in exponential way with mean 30 minutes. What is the meaning of this line? It is question number 6 of your book. What is the meaning of this? That the service time follow the exponential distribution with parameter mu. And what is the value of the mu? Mu is the service rate. Mu is service rate. And 30 minutes is given to you as a mean service time. Mean service time. So if you want to write from the given information, so 1 upon mu is given as a 30 minute. 30 minute. So mu will become the 2 per hour. 2 per hour. If arrival of the TV sets is paisa with average rate of 10 per 8 hour, means the arrival follow the paisa process. So if arrival follow the paisa process, it means inter arrival time follow the exponential distribution with the rate means lambda, with the rate lambda, and lambda is what? 10 per 8 hours, means 10 by 8 per hour TV sets. So which model it is? Inter-arrival time follow the exponential, service time follow the exponential, single server. If nothing is given, always we assume that it follow the FCFS. If there is no limitation of the capacity or population, then always we assume as a infinity. So this is the MM1 infinity model. Now you have to find the find the repairman's idle time each day. So you have to compute the idle time. So before computing this, we have computed the lambda is equal to 10 by 8 and mu is equal to as a 2. So rho is equal to what? Lambda upon mu. So it is the 10 by 8 upon 2, that is the 10 by 16, 10 by 16 or 5 by 8 or the 5 by 8. Now if you have to compute, find the repairman's idle time each day. So here we have the idle time is what? Proportion of time. The proportion of time server is idle, right? So it is the 1 minus P naught. No, it is the P naught. Proportion of the time system is server is idle. That is the P naught. So P naught is what? 1 minus rho. 1 minus rho is what? 1 minus, we have the 5 upon 8, that is the 3 upon 8, right? 3 upon 8. So if that it is in the question, it is given to you that day is of 8 hours. So idle time will become 3 hours. Idle time, idle time is given to you as a 3 hours. Find also the expected line length. Expected line length means what we have to compute. We have to compute the L. Expected line length, it means we have to compute the L. And L is what? Rho upon 1 minus rho. Just now we have computed. So it is the 5.8, 5.8 upon 1 minus 5 upon 5 upon 8. So that is the 5 upon 3. That is the 5.3 TVs. So 1 upon that is the 5 upon 3 TB. So on an average, there are 5.3 TBs in the system, in the shop. So in this way, we can compute the expected number of TVs in the system.
So here, why have we calculated for line length? Why have we calculated L and not LQ?
Line length means here we are talking for the number of TVs in the system. So one customer, one TV which he is repairing, that is also in that system.
So, but like line usually means only the people who are waiting, right? Except for the, I mean, this thing, except for the one who's being serviced, is everyone else who's waiting. That's what we generally say by line length, right? So in this case, line length means we have to include the one getting repaired.
That we have to include. Actually, that is also in line.
Okay, so
Here we have computed, but LQ. Whatever you are talking, that is here. Right? Whatever you are talking, that is here.
yes, sir. Okay.
Right? So in this way, we solve the okay. In next class, we start this question. Right? Because it takes the time. So in next class, better we solve this system. Any other doubt?